There's a lot of chemistry that you should recall from 1201 and 1202 that you are going to be using in organic, and this chapter goes over a lot of that. Now, it's a cursory review. It's not a detailed review. If, as we go through this, you see something that you're like, I have never seen this before, you might need to get a little extra help in understanding the material so that you have a good foundation for learning organic. You know, here's the basic atom and how it's put together. There's protons and neutrons in the nucleus and electrons in the cloud around it. The number of protons determines the element, and the number of electrons is equal to the number of protons when it's neutral. Additional electrons give it a negative charge. A reduction in electrons give it a positive charge. Variations in neutrons give rise to isotopes, and then you have the atomic mass, that is the average mass of atoms of that element. Real basic stuff that you should recall from general chemistry. Now, the electrons in the electron clouds actually are waves. They're both particles and waves, but the wave characteristic of it is very important. This is why when orbitals overlap, they actually can interact and form a bond because they're waves. The wave function is given the symbol phi right here, and that's where the electron is most likely to be. It's basically a probability of finding the electron. The wave function is the probability is phi squared, but the wave function is where we find the electron. So this is real important. Defining the wave function is real important to describing the electron mathematically. Now, we're not going to be doing that in organic, but sometimes you'll see this symbol, and we'll talk about the wave function and how electrons interact as waves. The electrons in various orbitals have different shapes. Their wave functions have different shape. So S orbitals have this spherical shape here. P orbitals have this double-lobed shape. The D and F orbitals are important in chemistry, but in organic chemistry, we're talking about first and second period elements primarily. And so the S and P orbitals are what we're most concerned with. Orbital energies, these are the major orbital locations, energy locations for electrons for the first three periods. And you can see that we have S, 1s, 2s, 2p, 3s, 3p, 3d. If this is not familiar to you, then you probably need to come and get some help and learn some additional material. I'm not going to go into this in detail. This is just what I'm trying to do right here is jog your memory to get you to remember, oh yes, electrons reside in these places, and we have particular electron configurations. The p-orbitals are real important in organic chemistry because the overlap with the p-orbitals give rise to pi bonds, and those pi bonds make up many of our functional groups. So a p sublevel has 3 p-orbitals in them, and they're what we call degenerate energy, meaning they have the same energy, they just point in different directions. And notice there's this planar node that is at the nucleus. So right here's the nucleus, and there's a plane passing through it where the electron never is there. And this side is detached from this side, and the electron is actually found over on this side and over on this side at the same time. So this is a wave function. The reason that we give them different colors is that we might say that the blue side is positive and the red side is negative. And we're not talking about charge, we're talking about where the wave is with respect to the origin and how it might overlap, being either positive or negative in its sign of the wave function. If you don't understand this at this point because you did not have much of this in 1201, it's okay, because when we go to use these orbital shapes and talk about the nodes and overlap, we'll review this area. It's basically, you do need to know that there are 3 p orbitals and they're at 90-degree angles to each other, and there is a node at the nucleus. Electron configuration comes by building the electrons up from the lowest possible place and then filling it up higher. That's called the Aufbau principle. The Pauli exclusion principle is that you can only have 2 electrons in any orbital maximum, and that when they occupy the same orbital, they have to have opposite spin. And then Hund's rule is electrons will spread out into separate orbitals if they're all at the same energy. So 3 p orbitals, 3 electrons will occupy those 3 orbitals separately instead of piling up in, pairing up in one of those orbitals. So it just means they spread out into separate orbitals when they can. Okay, so now what I want you to do is stop and figure out what is the electron configuration of each of these elements, just to check your understanding and see if you remember this correctly. Pause this and go ahead and answer, and then we'll go through the answers to make sure that you have this correct. All right, the electronic structure of carbon is 1s2, 2s2, 2p2. For oxygen, 1s2, 2s2, 2p4. Nitrogen, 1s2, 2s2, 2p3. Hydrogen is just 1s1. Phosphorus has gets into the n=3 level, so it's 1s2, 2s2, 2p6, 3s2, 3p3. And then sulfur is like phosphorus, except the valence shell is 3s2, 3p4. Now the valence shell of each of these is going to be the highest n number electrons. So if you look up here at carbon, you can see that carbon has n=2 is the highest n number, so all of n=2 is this valence shell, 2s2 and 2p2. If I look at oxygen, the valence shell is 2s2, 2p4. Nitrogen, 2s2, 2p3. The entire electron structure of hydrogen is its valence shell. The 3s2, 3p3 is the valence shell of phosphorus, and for sulfur it's 3s2, 3p4.